Hello, hello. Hello everyone, very good evening. I welcome you all. Okay, so this is the 11th lecture of discrete mathematics and we are discussing set theory and algebra. What did we discuss in the last class? In the last class, we have discussed the basic concepts related to group theory, that what do we mean by algebraic structure. So, a set S with respect to binary operation asterisk will be an algebraic structure if it is closed. Clear? Now, semigroup, sir, it should be closed plus associative. For a monoid, it should be closed plus associative plus identity should exist in this set with respect to binary operation asterisk. So for group, it should be closed, associative, identity should exist, and inverse of every element of the set must be present in the set itself. And finally, when do we say that the group is an abelian group? If all these four properties along with commutative property is satisfied. So these are the things related to group theory. I hope you understand each and everything clearly. We have already discussed all of them in the last class. Now, what are we going to discuss in the today's session? So today we are going to understand the concept related to finite groups. So what actually we mean by finite groups? What are the finite groups of real numbers with respect to addition and multiplication? That's what we'll see. Apart from that, we'll see that what is the reason because of which the other finite groups of real numbers are not possible with respect to addition and multiplication. So what we will try to do, sir, we will try to uh, include the imaginary numbers to create some more finite groups of with respect to multiplication, or otherwise we will try to change the operation. So one operation which is defined is addition modulo operation, addition modulo with respect to number m, and multiplication modulo operation with respect to integer m. Apart from that, for a finite group, we will try to understand what is the order of an element of the group. So in a group, if we have an element A, so what is the order of that element? That's what we'll try to understand. What do we mean by the order of an element? So anyway, as of now, all these terms may look unfamiliar, but as we proceed, you will understand the meaning of each and every term in proper detail. So let's understand the concept of finite group. When do we say that the group is a finite group? So let's try to understand. If I say that's a set of all integers with respect to addition is a group. Yes, sir. We know that set of integers with respect to addition is a group. But in this group, this set of integer is an infinite group. Why? Because there are infinite set. So because this set is an infinite set, therefore this group is an infinite group. Now, what do we mean by finite group? So finite group is a group whose underlying set is finite. Whose underlying set is finite. If the size of the set is finite and it still follows the property of a group with respect to some binary operation asterisk, then it will be called a finite group. Okay, so we'll try to understand the example. Now, if we have a finite group, we will also define the order of the finite group. So if it is a finite set, if the underlying set is a finite set, then we will know that how many elements are there in that finite set, and the number of element in the finite set will define the order of the finite group. So number of elements in the underlying set defines the order of group G. So generally I denote it using order of G. Okay. Anyway, so let's look at some examples. So please try to understand, if I take a set containing element 0, if I take a set containing element 0, then this is a group. Now, how many elements are there in this set? Sir, only one element. Therefore, what will be the order of the set? Sir, is a group of order 1, is a group of order 1 with respect to addition. Clear? So please try to understand, is this statement correct? So no matter how many times I add 0 with 0, no matter how many times I add 0 with 0, result will be 0 itself. That means this set is closed with respect to operation addition. Apart from that, addition is associative. Addition is associative. Now, identity element with respect to addition is 0 and 0 is present in this set. Therefore, identity element exists in the set. Now, inverse of identity element will always be identity element. Therefore, inverse of 0 is 0 and it is present in the set. Inverse of 0 is 0 and it is present in the set. Therefore, it is a group. Therefore, it is a group of order 1 with respect to addition. But again, the set containing element 0 cannot be the group of order 1 with respect to multiplication. We simply know that identity element will be 1 which is not present in the set. Even if we include 0 in our set, then it can never be a group with respect to multiplication, because inverse of 0 will never exist with respect to multiplication. Why? No matter what number is multiplied with 0, result will be 0. It can never become 1. And identity element is 1. So, two elements are inverse of each other if their binary operation comes out as the identity element. But with respect to multiplication, identity element is 1. So, no matter with what element we multiply 0, result will never be 1. Result will never be 1. Therefore, inverse of 0 does not exist with respect to multiplication. Okay. If I have a set in which I include element 1, so 1 is the identity element with respect to multiplication. So we know no matter how many times we multiply 1 with 1, result will be 1. It will be close with respect to multiplication. Multiplication is associative. Identity element with respect to multiplication is 1, and inverse of 1 will be 1 with respect to multiplication. So 1 is a group of order 1 with respect to multiplication. All the properties are satisfied. All the properties of the group are satisfied. Okay. Can we create any other finite group of real numbers with respect to addition? Now the problem is, if I have any other number apart from 0, let's say assume if I take x, then x plus x will become 2x. So if I add x, I will also have to include 2x, because 2x and x both are present. Therefore, I'll also have to include 3x. 3x plus x is also present. So I'll also have to include 4x. So if I take any other element in the set apart from 0, and if the operation is addition, then eventually the set will become infinite in order to make it a closed set with respect to binary operation addition. So we cannot create any other finite group of real numbers with respect to addition apart from this group containing element 0. Now, is it possible to create some other groups or other finite groups of real numbers with respect to multiplication? So please try to understand that, sir, okay, 1 is one set, but apart from that, we also have two elements, 1 and minus 1. No matter in what order we multiply 1 and minus 1, and no matter how many times we multiply 1 and minus 1 with each other, result will be either 1 or minus 1. That means the set containing element 1 and minus 1 will be closed with respect to multiplication. So first property is satisfied, that it is closed. Apart from that, multiplication is associative. Now, identity element with respect to multiplication is 1 which is present in the set. Now, Sir, what will be inverse of 1? So, as I told you, inverse of identity element will always be identity element. Why? Because 1 asterisk 1 will be 1, which is the identity element. Therefore, 1 and 1 are inverse of each other. Similarly, what will be inverse of minus 1? So, the idea is with what? So, this basically multiplication, don't get confused. 1.1. So with what element we multiply minus 1, that the result comes out as the identity element. So this question mark must be minus 1. Therefore, inverse of minus 1 will be minus 1. So set is closed with respect to multiplication, associative, identity element is present, and inverse for every element of the set is present in the set itself. So it is also a group. It is satisfying all four properties of a group, and the number of elements in this set are 0. Therefore, it is a finite group of order 2. So 1 comma minus 1 is a group of order 2 the group of order 2 with respect to multiplication. Now, we cannot create any other group of real numbers with respect to multiplication apart from this two groups. One is the set containing the identity element, another is the set containing 1 and -1. So these are the only two finite groups of real numbers with respect to multiplication. So let's on this point. So 0 with respect to addition form a finite group of order 1, 1 with respect to multiplication form a finite group of order 1, -1 comma 1 with respect to multiplication form a finite group of order 2. Now, above 3 are the only finite groups of real numbers. Are the only. We don't have any other finite group of real numbers with respect to multiplication and or addition. So, with respect to multiplication and or addition. So, then what we need to do? So, sir, if we don't have any other finite group of real numbers, then the only choices which are available to us are move from real numbers to some other types of numbers. So basically that will be nothing but imaginary number, and otherwise try to change the operation, try to create some other operations apart from multiplication or addition. So that's what we are going to do. So the very first example which we are going to take is cube root of unity. So what are the cube roots of unity? Sir, cube root of unity are 1 omega and omega square. Sir, what do we know? 1 plus omega square is equals to 0. That's summation of the root is equals to 0. Apart from that, we know that omega cube is equals to 1. So these are what we know from our childhood mathematics, right? So 1 omega and omega square are the cube roots of unity. These are omega is not a real number. So anyway, the cube root of unity 1 omega square form a finite group. Form a finite group. How many elements are there in this set? So 3 elements. Form a finite group of order 3 with respect to multiplication. So the reason is quite simple. Why were we not able to create any other group of real numbers with respect to multiplication or addition? Because apart from 0, if we take any other element, it will not be closed. Apart from a set containing element 1 or a set containing element 1 and -1, if we include any other element in the set, then it will not remain closed with respect to multiplication. If you include x which is not equals to 1 or -1, then x into x will be x square. It will be different from x. Similarly, x square into x will be x cube. It will again be different from x and x square. So that's the idea, that the set will not remain closed if we include any other type of element. But in case of 1 omega square, if we try to multiply 1 omega square with each other in any manner, then the moment the number becomes omega cube or more than omega cube can be converted into 1, and this set 1 omega square will remain closed with respect to multiplication. So the problem that arises in a finite group with respect to addition or multiplication is the closure property, that we are not able to satisfy the closure property in order to create a finite group of real numbers with respect to multiplication or addition. So that's what we are trying to solve here, that 1 omega and omega square form a finite group of order 3 with respect to multiplication. So will it be closed? Yes, sir. Closed, yes, as omega cube is equals to 1. So that's what you need to understand. The moment power becomes more than omega becomes omega cube or more than omega cube, you can convert omega cube into 1 and it will automatically boil down into one of the 3 elements, 1 omega and omega square. Okay. Next, associative. Yes, sir. Yes, multiplication is associative. We don't worry about the type of element. Multiplication is associative. Okay, identity is present, sir. Identity with respect to multiplication. Identity with respect to multiplication is one which is present in the set. Now, the only thing that we need to understand is, sir, what will be the inverse? In order to understand the concept of inverse, we'll create one table called composition table. What are the elements? Sir, The elements of the set are 1, omega and omega square. 1, omega square. This is your operation. What is this? Multiplication. Now, let's check. Sir, 1 into 1 is 1. 1 into omega is omega. 1 into omega square is omega square. Similarly, omega into 1 will be omega. Omega into omega will be omega square. Omega into omega square will be omega cube. And we know omega cube is nothing but 1. Similarly, omega square into 1 will be omega square. Omega square into omega will be omega cube 1. Now, omega square into omega square will be omega raised power 4. As I told you, omega raised power 4, so it can be written as omega cube into omega. So it will be 1 into omega. It will be 1 into omega, that is, it will become omega. Now, let's look for the identity element. So, the identity element with respect to multiplication is 1. Clear? So, let's look for the identity elements in this composition table. So, here 1 is the identity element. So, this two will form the inverse of each other. So, inverse of 1 will be 1. So, where else here is the identity. So, this two form the inverse of each other. That is, inverse of omega will be omega square, because if omega multiplied with omega square, it will give you omega cube, which is equals to 1, which is the identity element. So, if the binary operation of two elements results the identity element, then those two will be inverse of each other. Clear? Now, omega square and omega will give you the identity element. That's the same concept. You are not getting anything new. Omega and omega square are the inverse of each. So, if we talk about inverse, we just need to check whether inverse exists for every element or not. So, inverse of 1 will be 1. Inverse of omega will be omega square. And inverse of omega square will be omega. So, inverse also exists for every element of the set within the set itself. Therefore, all four properties of group are satisfied with respect to multiplication. Therefore, 1 omega omega square will form a finite group of order 3 with respect to multiplication. Now, okay, so we are done with omega 1 omega omega square. Sir, these are the cube root of unity. What are the 4 roots of unity? Sir, 4 roots of unity are 1, minus 1, iota and minus iota. 4 root of unity are 1, minus 1, iota and minus iota. The set of 4 roots of unity, that is 1, minus 1, iota and minus iota, will also form a finite group, but there are 4 elements, so will form a finite group of order 4 with respect to operation multiplication. Sir, what do we know? Summation of the root will be equals to 0. So, 1 plus minus 1 plus iota plus minus iota will be equals to 0. And iota square will be equals to minus 1. That's what you must know from your childhood mathematics, that iota square is actually nothing but minus 1. Okay, now no matter in what order we multiply 1, minus 1, iota and minus iota, the moment this becomes iota square, it will degenerate into minus 1. That is, this set of 4 elements 1, minus 1, iota and minus iota will always remain closed with respect to multiplication. So, the first property, that is closure property, is satisfied. Yes, sir, it is closed. Operation multiplication is associative. Yes, sir, multiplication is associative. Identity is present. Identity with respect to multiplication is 1, which is present in the set. Now, the only problem is with respect to inverse, that we don't know whether inverse of every element of the set is present in the within the set or not. So, again, as I told you, whenever you are checking for inverse, you can simply use the concept of composition table. So, have it 1 minus 1 iota minus iota, 1 minus 1 iota minus iota. Operation is nothing but multiplication. Okay, now look for the values. 1 into 1 will be 1, 1 into minus 1 will be minus 1, 1 into iota will be iota, 1 into minus iota will be minus iota. minus 1 into minus 1 into 1 will be minus 1, minus 1 into minus 1 will be 1, minus 1 into iota will be minus iota, minus 1 into minus iota will be plus iota, or simply iota. Now, iota into 1 will be iota, iota minus into minus 1 will be minus iota, iota into iota will be iota square is actually minus 1. Iota into minus iota will be minus of iota square, that is minus of minus 1, minus of minus 1, which is 1. Okay. Minus of iota into 1 will be minus of iota, minus of iota into minus 1 will be plus of iota, minus of iota into iota will be minus of iota square, which is already calculated. Minus of iota into minus of iota will be plus of iota square, that will be minus 1. Now, if we look for the identity element, so here is the identity element, therefore 1 inverse of 1 will be 1. Inverse of 1 equals to 1. Now, here is the identity element, therefore inverse of minus 1 will be minus 1. When we perform the operation of minus 1, the result is 1, therefore inverse of minus 1 is minus 1. No. Sir, here iota and minus iota produces the identity element, therefore inverse of iota is minus iota. Inverse of iota is minus iota. Similarly, by complementation rule, inverse of minus iota will be iota. Inverse of minus iota, iota. So inverse is present for every element of the set within the set itself. Therefore, inverse property is also satisfied. Therefore, it is also a group, or I would say finite group of order 4 with respect to multiplication. Now, if I take any nth root of unity, set of n roots of unity will form a finite group of order 4 with respect to multiplication. Respect to multiplication. Yeah, this one thing. But anyway, sir, we are anyway not much comfortable with this omega square value or iota minus iota value. So we do not look for fifth root of unity, sixth root of unity. I mean, in general, even I don't know what are the fifth root of unity and sixth root of unity. I never tried to learn about them because it is beyond our scope. So ultimately, we understand that okay, there are only 3 groups of real numbers. There are only 3 finite groups of real numbers with respect to addition and or multiplication. We may create some more finite groups of imaginary numbers with respect to multiplication. But again, they are imaginary numbers. What are we doing? So, what can we do then? If we want to create some other finite groups, then what should we do? So, in order to create some other finite groups of real numbers, we will have to change the operation. Okay, so there are 2 types of operations are defined. One is addition modulo m operation, another is multiplication modulo m operation. So what is addition so these are some basic properties. So in a group of order 1, if there is only one element in the set, then it is guaranteed that that element will be identity element, because if identity element itself is missing, then it can never become a group. It can never become a group. So in a group of order 1, the only element of the group is the identity element with respect to that binary operation. So simple statement. Apart from that, if we have two elements in the set, so please try to understand, whenever we have 2 elements in the set, then one of those elements will be identity element. If it is a group, it is guaranteed that one of those 2 elements will be identity element and another element is, let's say, A. So we know that inverse of identity element is, inverse of identity element will be identity element itself. Now, what can be the inverse of this other element if it is a group? If it is a group, then we know that the inverse of second element A exists. Now, inverse of A cannot be the identity element. Why? Because inverse are always in the pair. So, if inverse of A is E, then inverse of E has to be A. But we know inverse of E is E. Then, what can be the inverse of A if inverse of A is guaranteed to exist? Sir, if inverse of A is guaranteed to exist, then inverse of A can be A only. An inverse of A can be A only, and it is guaranteed that the inverse of A will exist because it is a group. It is already being said it is a group. So inverse of every element will be present in the set itself, right? So in a group of order 2, every element is inverse of itself because identity element is the inverse of itself. So the another element will have to become the inverse of itself. There cannot be any other inverse of that second element, not an identity element. Okay, so these are two basic properties. Now let's move to the next operation, that is addition modulo m. So we are trying to define a new type of operation. Let's try to understand this. So it's nothing but simple modulo operation. So what do we know about modulo operation? Modulo operation gives remainder. So what will be the output of the modulo operation? The modulo operation will produce the remainder. What let m is any fixed positive integer, any. So whatever you are saying that if addition modulo m we are talking about, then this m is a fixed positive integer. Or a and b as any two positive integers, if we have, or rather I would say non-negative integer, positive will confuse because 0 is also allowed. 0 is also allowed. So for A and B are any two non-negative. Don't call it positive. Call it positive. Call it non-negative. Are any two non-negative integer. So A and B are any two non-negative integer. Then how do we define the binary operation addition modulo m with respect to two non-negative integers A and B? That is nothing, but we will simply add A and B and then we will divide it by m. Whatever the remainder is, that will be the result. So if I try to define this, then please try to understand. If we divide A plus B by m, then it will eventually depend on the value of A plus B. If the value of A plus B is less than m, if value of A plus B is less than m, then the remainder will be A plus B. The remainder will be A plus B only. So if A plus B is less than m, then remainder will be A plus B. But what if A plus B is more than m? So if it is more than m, then the result will be whatever the remainder is. If A plus B greater than equals to m, where r is the remainder obtained A plus B by m. So if we divide A plus B by m, then whatever the remainder is, that will be the result of this addition modulo m operation. So it's simple to visualize. Let's do this. Sir, if I have 2 addition modulo 7 with 4, so what will be the result? Sir, 2 plus 4 is 6. So here the value of m is 7 and the other two integers on which the binary operation is being performed are 2 and 4. So how do we define 2 addition modulo 7 with 4? So it will be nothing but 2 plus 4 modulo 7. So 2 plus 4 is 6, divide by 7, remainder will be 6 only. Remainder, if we divide 6 by 7, the remainder will be 6. The remainder will be 6. Now, if we have 2 addition, I have 4 addition modulo 7, 5. Now, if we perform the addition modulo 7 operation on elements 4 and 5, then 4 plus 5 is 9. 9 divided by 7, the remainder will come out as 2. This is how the binary operation addition modulo m is defined. Please try to understand what is the problem with the normal addition or multiplication. The problem with the normal addition or multiplication is that as you keep on increasing the value, the result which is produced because of addition and multiplication will keep increasing. But if the operation is a modulo m operation, then the result of modulo m operation will always be between 0 and m minus 1, because the remainder produced by the modulo m operation will always be between 0 and m minus 1. If you divide any number by m, then the remainder can never be more than m. Remainder, it cannot be m itself. The remainder will always be between 0 and m minus 1. Therefore, the modulo m operation will ensure that the set remains closed. The value that we will obtain because of the operation of two element of the set never goes beyond m minus 1, clear? So that's the idea, that addition modulo m operation as well as multiplication modulo m operation will try to keep the set closed with respect to operation, because remainder will always be between 0 and m minus 1. Now let's try to define the multiplication modulo operation. So multiplication modulo m is denoted by this. How do we define this? So just in place of addition, we will try to perform the multiplication. So let m as any fixed positive integer, and a and b are any two positive integers, then a multiplication modulo mb will be nothing, but we'll simply multiply a and b and we'll divide it by m. Whatever the remainder is will be your output. So the remainder will be ab only if the value of a into b is less than m. This can be any value r if a dot b is greater than or equals to m. R is what? Remainder. Multiply a and b divided by m. Whatever the remainder is, that will be your output. Anyway, so let's take two examples. So if I have 2 multiplication modulo 7 or whatever, 2 multiplication modulo 2 will be what? So 2 into 2, 4, divide by 6. 2 into 2, 4, divide by 6. 4 is less than 6, therefore the remainder will remain 4. Now 2 multiplication modulo 6 with 5. Sir, what will be the result? Sir, 2 5s are 10. 2 5s are 10. Divide by 6. The remainder will come out as 4. So these are two operations, addition modulo m and multiplication modulo m operations, which will try to keep the set closed with respect to binary operation multiplication modulo m or addition modulo m. Now let's try to understand some important points, that if I take any set of real numbers from 0 to n minus 1, if I take the set of integers, or not real numbers, if I take the set of all integers from 0 to n minus 1, then it will always form a group with respect to addition modulo n. So that's your first note. What does it say? The set containing elements from 0 to n minus 1, the set containing elements from 0 to n minus 1 form a group with respect to addition modulo n. Come on, do you know that this set will remain closed no matter in what order you take to perform the operation on two numbers of this set? If you divide it by n, the remainder will be between 0 and n minus 1, and all the numbers between 0 and n minus 1 are present within the set. Therefore, this set will be closed. Now, addition is associative, therefore addition modulo n will also be associative. Addition is associative, therefore it's primarily based on the operation addition. Therefore, addition modulo n will also be associative. Please just count. First one, set is closed. Second, addition modulo n is associative. Okay. Sir, we know the identity with respect to addition is 0, but what will be the identity with respect to addition modulo n? Now my question is, if this number x, let x is less than n, so what should we add with x such that if we divide it by n, then the remainder is x only. The remainder is x only. Now, sir, this x is already less than n. If we do not add anything into this and simply divide it by n, then the remainder will come out as x only. That means x addition modulo n with a 0 will be equals to x only. So if the operation of two elements, if the operation of any element with a particular element is that element itself, then we say that that other element is nothing but the identity element. Simple definition of identity element. So if we perform the binary operation addition modulo n of 0 with any number x, then the result will remain x itself. Therefore, the identity element with respect to binary operation n is with respect to binary operation addition modulo n is 0 only. So, identity element with respect to addition modulo n is 0. And 0 is present in this set. That's the thing. 0 is present within the set. Now, the last thing that we need to understand is inverse. So what do we know? Sir, one thing that is known as inverse of identity, that is inverse of 0 will be 0 only. That is inverse of identity will be identity element itself. For any other element, x belonging to set, for any other element x belonging to set, what will be inverse of x? What will be inverse of x? Sir, with x, so let's look at this. Try to understand this. Sir, inverse of 0 will be 0. Now, 1 plus n minus 1 will be n divided by n. Remainder will come out as 0. Therefore, inverse of 1 will be n minus 1. Inverse of 2 will be n minus 2, because 2 plus n minus 2 will be n divided by n. Remainder will be 0. That is identity element. So, for any element x, the inverse of x will be nothing but n minus. For any element x, the inverse of x will be nothing but n minus x. And if x is present in the set, then n minus x will also be present in the set, because x is between 0 and n minus 1. Clear? So inverse will also exist for every element of the set. So let's take an example. Take an example. If I simply say 0, 1, 2, 3, 4. Sir, these numbers are 0 up to 5 minus 1. These numbers are from 0 to 5 minus 1. So, 0, 1, 2, 3, 4 will form a finite group. Will form a finite group of order. How many elements are there in the set? There are 5 elements. Will form a finite group of order 5 with respect to what operation? Sir, the elements are between 0 to 5 minus 1. Therefore, the operation will be addition modulo 5. Do you check that? Sir, this will be closed in what order we perform the binary operation addition modulo m on any two element of this set, it will remain closed. So, it is closed. Operation is associative. Identity with respect to addition modulo 5 will be 0. Inverse of 0 will be 0. Inverse of 4 will be 1. Inverse of 2 will be 3. Yeah. So, inverse of 0 is 0. Inverse of 1 is, inverse of 2 is 3. Inverse of 3 is 2. If you do not understand this, then let me explain the way also. Please check this. So what will be one addition modulo 5 with the one addition modulo 5 with 4 will be nothing but 1 plus 4 divided by 5. Whatever the remainder obtained from 1 plus 4 divided by 5. So 1 plus 4 is 5 divided by 5, remainder 0. So here 2 addition modulo 5 with will be what? 2 plus 3, 5 divided by 5, remainder 0. 3 and 2, 3 addition modulo 5 with nothing but 3 plus 2, 5 divided by 5, remainder 0. Similarly, 4 addition modulo 5 with 1, 4 plus 1, 5 divided by 5, remainder 0. So all of them are producing the identity element when we perform the binary operation on those two elements. Therefore, they are inverse of each other. Therefore, they are inverse of each other. So that's a basic definition. If you take any set, from, sorry, not Sunny, if you take the set of all integers from 0 to n minus 1, then it will always form a group with respect to addition modulo n. Similarly, we'll define the concept with respect to multiplication modulo n. So let's look at the second note of discussion. Let n is any positive integer. It can be any positive integer. Here the definition is quite clumsy, so please try to understand this. Let n is any positive integer. Now, if I take the set that contains all the elements which are all the positive integers which are less than n and co-prime to n. So, the set of all elements, not all elements, yes, the set of all elements which are less than n, or rather again, there is a problem in the definition. So, the set of all positive integers will not include 0. Set of all positive integers. Set of all positive integers which are less than n, so such that those positive integers are less than n and co-prime to n. Sir, what do we mean by co-prime? Two numbers m and n are said to be co-prime. Two numbers m and n are said to be co-prime if the greatest common divisor of m and is nothing but 1. So that means co-prime or relatively prime. Another term is relatively prime. So we are not saying that the numbers are prime numbers. We are not saying that the numbers are prime number, but they are relatively prime to each other. That means the greatest common divisor of those two numbers equals to 1. So what's the idea? It simply says that if n is any positive integer, then set of all positive integers. So positive integers will be 1 or more than 1. Positive integers will be 1 or greater than 1. They cannot be 0, they cannot be negative. So set of all such positive integers, which are less than n and co-prime to n, form a group with respect to this n is any positive integer. So with respect to multiplication modulo n, let me explain. If not clear, then please try to understand. Example, let n equals to 8. Let n equals to 8. Then can you list all the numbers which are less than 8 and co-prime to 8? Set of all positive integer less than 8 and of all positive integers. I believe I have some power issue. But make sure that do not lose connection. If we lose connection, then we'll start the same topic in the tomorrow's class. Power backup. So set of all positive integers which are less than and co-prime to 8 will be what? Sir, 1 is less than 8 and co-prime to 8? Yes, sir. 2 and 8 are not co-prime because the GCD of 2 and 8 will be 2. 3 and 8 will be co-prime because the GCD of 3 and 8 equals to 1. There is no common divisor of 3 and 8 apart from 1. Now, 4 and 8 are not co-prime. The GCD of 4 and 8 will be 4. But 5 and 8 are co-prime. The GCD of 5 and 8 will be 1. 6 and 8 are not co-prime because the GCD of 6 and 8 will be 2, not equals to 1. But 7 and 8 are co-prime. Now 8 is not included because we are saying set of all numbers which are less than n. So first of all, in the set we cannot have any number which is n or more than n. So this is the set of all numbers such that the number are less than n and co-prime to n. So what do we know? Therefore 1, 3, 5, 7 form a group with respect to multiplication modulo 8. If you want, you can check. Sir, take any two numbers in whatever order and perform the operation multiplication modulo 8. The result will be within the set. Sir, 1 into 1 divided by 8 remainder 1. 1 into 3, 3 divided by 8 remainder 3. 1 into 5, 5 divided by 8 remainder 5. 1 into 7, 7 divided by 8 remainder 7. Then 3 into 1 will be same. 3 3s are 9. 9 divided by 8 remainder 1 within the set. Close. So 3 5s are 15. 15 divided by 8 remainder 7 within the set. 7 3s are 21. 21 divided by 8 remainder will be 5 within the set. Now let's look for 5. Sir, 5 we have already checked 5 with 1 and 3. So 5 5s are 25 divided by 8 remainder 1 within the set. 5 7s are 35 divided by 8 remainder 3 within the set. Done. 7. Sir, we have calculated 7 with 1 3 and 5. 7 7s are 49 divided by 8 remainder 1. So that's okay. So we know that the set is closed. Note, set is closed. Yes, sir, set is closed. Okay, so multiplication is associative, therefore multiplication modulo n is associative. Multiplication modulo n is associative. Third one, sir, identity element with respect to multiplication modulo n will be what? Sir, identity element with respect to multiplication modulo n will be 1 because if x is less than n, then x multiplied with what? And divided by n, the result should be x. So if x is already less than n, then if it remains x and if you divide it by n, the remainder will come out as 1, remainder will come out as x only. So this question mark must be 1. Therefore, identity with respect to multiplication modulo, write down on the previous slide. What, sir? Multiplication modulo n is associative